And so thank you, everybody, for being here and for welcoming me. So let's hope this clicker works. Hey, there we go. All right, so I'm going to be talking about enabling quantum communications through advanced single photon detection technologies, which is certainly a mouthful. I'm going to start out brief overview of the company, tell you a quick story about how we came to be, and hopefully we'll be able to get into it from there. So ID Quantique was founded way back in 2001, which makes us an elder statesman in the quantum community. You know that we are an original quantum company because we have 2 Qs in our name, where most of you guys just have 1 Q in your name. So we were founded by 4 quantum physicists from the University of Geneva. We're up to a bit over 100 employees now, primarily located at our headquarters in Geneva, Switzerland. We do have another rather large office in Seoul, South Korea. I myself am based in Boston to help identify and support our customers or users in North and South America. So our company is built into 2 main business units. We have quantum safe security, so that's the side of the business that many of you might be familiar with that makes the QKD boxes. So we make fully fleshed out QKD platforms. You put one in one location, you put Alice in one location, you put Bob in the other location. They talk to each other over a secure quantum channel, and they make quantum keys so you can secure, just as we've been talking about here, we can secure traffic end to end. The other side of the business, which is the one that I work for, does quantum sensing. So we make single photon detectors and the associated electronics that support them. So a quick story that will hopefully provide some context for the rest of this talk. And I do promise to eventually I'll tie this together with networking and security, though it's not going to start that way. So IDQ was founded initially to realize the vision of commercially viable QKD hardware. So like many new technologies, it began with a scientific theory, which was then translated to a model of a physical system. So for those of you with any experience prototyping, R&D, people who design systems, you know that a model is really just a drawing on paper of some boxes. And each box represents a separate component. It could be optical, electrical, mechanical component. And you connect these components together, and you can hopefully create a system that's capable of performing some novel task. So when you're designing a prototype system, the goal is always to use as many commercially available, pre-existing, off-the-shelf components as possible, because doing so will save you lots of time and money. So when our founders laid out the first QKD system, the model of their first QKD systems, there was one box on their schematic that just said SPD, which stands for single photon detector. And this represented a problem because there weren't any commercially available telecom wavelength single photon detectors that you could buy at that point. So they had to develop their own. First, they identified an industrial partner, PLI, which is no longer PLI, but they bought some diodes from them, and they tinkered around with them and were able to actually make working in gas-based single photon detectors. And so in this way, we actually became our own first customer because we developed them so we could use them directly with our own QKD hardware. And the founders of the company also realized at this time that if this was interesting to us, maybe this would be interesting to other people. And there were lots of other scientists who were indeed interested in acquiring these. So these single photon detectors became our first products that were available for sale. And over the years, we've continued to be our own best customer for this particular product line. Every QKD box that we sell has these single photon detectors in it. And so as the quality of the detectors improves, so does the performance of our QKD products. So in this way, the business units of our company were not just tied financially, but also technically. And so an ongoing theme with all of this is that the quality of experimental results, and thus the speed you can iterate, your ability to publish results, it's all dependent on the quality of the components in your system. And there are many scientific fields that are currently leveraging quantum or ultra-low light phenomena, and that includes biology, chemistry, physics, material science, electrical computer engineering. And if you look at any of the experimental schematics for many of those fields. You'll see something similar to what our founders laid out. You'll see experiment on one side, and you'll see a box that says SPD on the other side. And so our job in the quantum sensing branch of ID Quantique is to make that as straightforward, as dead simple as it can possibly be, so people can focus on the important parts of their work. So now I will, if this goes, there we go. Okay, so now an example of this. Here is a schematic. So the important thing to see here is the second box from the left. It says an ultra-low loss, fully connected photonic circuit. In this case, it's a photonic quantum computer, but realistically, it can be anything. This was developed by a team of our users. Then the next box, it says temporal spatial demultiplexing fiber loops. That sounds like something out of science fiction. It's really a fancy way of saying different length fiber loops to spread the photons out in time a little bit. And then you have, finally on the right, you have the superconducting nanowire single photon detector readout. So that's the part that we're responsible for. And yeah, as just a quick aside, it is widely accepted that the readout circuitry for many types of quantum computers can be based on single photon detection. So a lot of people in the quantum computing world here have probably talked to us or some people like us in the recent past. Okay, so here are some of the most active fields that are developing experiments that are configured in the way that I just showed you. Something to mention here is not all of these fields are actually directly analyzing quantum phenomena like entanglement or interference. Some of the life science applications here, like imaging and microscopy there, they just rely on the ability of single photon detectors to accurately measure incredibly low levels of light. So this is being put to use in methods like confocal microscopy, fluorescence lifetime measurement. Single photon detection can also be a very powerful tool for range finding applications. So that one that comes to mind immediately for most people is LiDAR. But another one is OTDR, or optical time domain reflectometry, which is a method of characterizing fiber optic networks and also assessing their health. So lots of different uses for single photon detectors. And so which industries do these R&D activities support? We like to think all of the important ones, all the ones that we like to spend time thinking about: energy, industry, chemistry, pharma, finance, public safety. Lots of different fields can, of course, benefit from the research being conducted by our users. And so, of course, that brings us to the quantum internet, which is what many people here are very interested in, spend a lot of time thinking about. So it's one of the most relevant unified goals of the quantum optics and related fields. People might have different definitions of what the quantum internet means, but I think we can all agree one of the underlying principles will be that information should be transmitted securely using single photons, which they may be encoded with additional information via polarization or entanglement, compared to the current method of optical communication, which relies on modulated pulses of light containing many millions of photons. The problem with this current method, of course, being that you can siphon off some of these photons without destroying the signal, and you can eavesdrop very easily on classical communications. So yeah, the quantum internet is going to contain many building block components that you can see. You have the quantum relays, the memories, quantum repeaters, et cetera. And one common theme in the development of all of these different components is that the people working on them need reliable single photon detectors in order to push their work forward. And just a quick story time based on some recent things. I was visiting some of our friends at UC Berkeley right up the road yesterday. And so I was in a couple labs, and some of our users are there. It's always nice seeing people who we've been working with for a couple of years. And my main takeaways of this visit were that there are a lot of really smart people working really hard to solve a lot of these problems, which is really cool to see in person. Emailing with people, seeing them on Zoom is one thing, but going into their lab and seeing the work that the grad students are pouring their lives into is a whole other thing. The other is that the grad students in these labs seem to be limited by access to high-quality single photon detectors. So in principle, they could work much faster if they had more detectors available to them. The most direct comparisons I can come up with for anyone who's familiar with these other fields, but it's kind of like NMR machines in chemistry or MRI machines for neuroscience. These are the tools that everybody wants access to so that they can do their experiments. So IDQ has been a partner, and we've been a part of many of the early breakthroughs contributing to this future quantum internet. Right now, we do in the world today have point-to-point quantum channels, including the ones that ID Quantique makes ourselves, our QKD platforms. We're working with researchers who are trying to, currently developing the next generation of quantum sensors and components, things like that. And we hope to participate in all of the future generations of this hardware as it comes to fruition. So I would be remiss if I did not talk a little bit about the products that ID Quantique actually makes to support this. So I like to think of us as the only full line supplier of single photon detectors, that meaning that we make everything from inexpensive room temperature SPADs, so in the upper left corner there, those are devices you just plug into a wall, you turn it on, you couple light to it, it makes a click every time it sees a single photon. They're really easy to use, the performance can be pretty good. At the other end of the spectrum, no pun intended there, I guess, the other end of the spectrum, we make SNSPDs, which are kind of the highest end solution for detecting single photons. And those are for the most demanding applications where you need very high quantum efficiencies, very high timing resolutions, things like that. And to round it all out, we also produce timing electronics, which helps you make sense of your single photon signals. And we have some lasers and things like that as well. So just to dive a little bit deeper into our superconducting nanowires, I feel like I should spend a few minutes talking about this because it's a rapidly growing part of our business. We've been installing these systems all over the world since about 2017. There's about 150 of them installed worldwide now, with 50 coming online every year. We have a relatively large team in Geneva who's exclusively dedicated to the development of various detectors and also the improvement of the cryogenic systems. And so this is a product that we are very, very much, we're pushing very hard on this program, and we're expecting to see it grow pretty rapidly over the next few years. And we make detectors for our SNSPDs at a wide range of wavelengths, going from the visible all the way into the infrared, so beyond 2 microns. The bread and butter for most people in the quantum communications world, of course, being the O band and the C band, and we have a number of detectors that support those wavelengths, including polarization agnostic detectors and also what we call P-SNSPDs or parallel SNSPDs that will give you photon number resolution capabilities. We have a couple different cryostats available, and we can package them all nicely into these integrated units for easy usability in your lab. So in addition to this, in addition to off-the-shelf products, we also do offer design services. We've partnered with companies, institutions to produce fully integrated photonic solutions. And we're expecting to continue growth as an OEM supplier as more quantum photonic products and systems make it to market. So if I go back, the guts of many of these devices are designed to be put into other people's devices. So if you're making quantum boxes that talk to other quantum boxes and you need single photon detection, this is one place to look for it. There we go. Okay, so in closing, we've been very fortunate to be here for over 20 years, to be able to contribute directly and to have a front row seat as the quantum revolution has gotten up to speed. And we're looking forward to collaborating with as many people at companies as possible moving forward to see where this really goes in the coming years. I think that I think we can all agree here that we're at a pretty serious inflection point, and it will be very, very interesting to attend conferences like this 5 years from now, see how it's grown. And so I think I've got a few moments for questions. I don't know what the timing is right now, but.
Yeah, great. Thank you for a very nice talk. So we have a couple minutes for questions. If there are any, yep.
Thank you, Noel.
I was just going to ask whether you think ID Quantique is going to get into the space between SPADs and nanowires at some point.
I think that we'll have no choice, right? If a technology presents itself that seems like it might supplant one of the existing technologies in either cost or performance, we're going to have to do it. And I think that our team is in a really good position to do it because of our various backgrounds, and we know the importance of this. So yeah, we're not going to let anyone get ahead. If there's a new technology out there, we're going to chase it down.
Yeah.
How large can be your photo detector? I mean, can you shoot the photon in 1 square meter and still detect it?
Oh, so the size of the detectors themselves is quite small. They're typically sized they live at the end of typically either a multi-mode or a single mode fiber. In most cases, a single mode fiber. So the detectors themselves are actually only microns in diameter. So in order to get your photons to couple them to the detector, you'll need some sort of collection optics.